Test? Oh, that sounds a lot better. Okay. Thank you. All right. So, yeah, I guess for those of you that are watching the recording, you might have missed the first part of the lecture, but you know it's more or less what was in the slides, so you wouldn't have missed that much. All right. So what I was saying here is that in some cases, the strategy, learning a good strategy for performing a task might actually generalize better than learning a model of the dynamics and learning a model of physics. And this is an example of that that's been particularly well studied for a strategy that humans employ to perform a particular task. So this is what's called the gaze heuristic. And the idea is that if you want to catch a flying object like a ball, the physics that govern that object are not too complex, but they're somewhat elaborate. You know, if it has air resistance, if there's wind and gravity and so on, then there's a fairly complex set of equations that governs how that object will move. But if you just want to catch it, then there is a very simple strategy that you can employ that doesn't require knowing about gravity or wind resistance, and that's what's called the gaze heuristic. So the idea in the gaze heuristic is very, very simple, and this is employed by humans, by athletes, and also by lots of different animals too. Very simple idea. If you have a flying object that you want to catch, you look at it, and you remember where it is in your field of view. So you basically like memorize its 2D coordinate in your field of view, and then you keep your eye fixed on it. And as you run, you just adjust your speed so that if it drops a little bit below where it was before, you speed up so that it goes back up. And if it rises, then you slow down. So if you follow this gaze heuristic, you can kind of see this, that the angle between the little guy there and the ground's the gaze angle stays the same. Then you can show with a very simple kind of similar triangles argument that you'll actually arrive at exactly the spot where the ball lands. So if it always stays in the same point in your field of view and you adjust your running speed so that it stays there, you'll get to right where it lands. So now if you've distilled this skill down into this strategy, now you can forget everything, not only about gravity and wind resistance, you can forget it even that it's a 3D environment. All you have to do is remember to keep that point in 2D in a fixed spot. So this is an example where the optimal policy will actually generalize better in general than a model of the environment. So this is maybe one case for why we might want to learn policies. And by the way, this is also something that you might learn about if you're flying an airplane or something like that. They might tell you, okay, find a little speck of dust on your windshield. If you see another airplane in the sky, if they're not moving relative to each other, then you're going to collide with that airplane. But if they're moving relative to each other, then you're going to pass each other safely. So kind of very, very simple geometric heuristic. Okay, so that's why we might want policies. So can we just set up our big computation graph like we talked about on Monday and backpropagate into the policy? So that's this picture. So if you remember here, this f of x comma u, that's our learned model. This pi is our policy, which for this picture I'm just drawing as a deterministic policy for simplicity. And c is our cost, which we might assume here is known. So then you can just compute derivatives of everything, compute the derivatives of the cost with respect to the action and state, backpropagate the derivative with respect to the state through the dynamics, and so on. And then you can compute the derivatives of the total cost with respect to theta, which are the parameters of your policy. So that's sort of the standard, set up a big computation graph in TensorFlow or Theano, compute, call the gradients function, get your gradients, and do gradient descent. It seems like a very reasonable idea once you have the dynamics. Very easy for deterministic policies to set this up. You can even set it up for stochastic policies. If you have a stochastic policy, you might use something called the reparameterization trick, for example. If pi is a distribution over some continuous variable, maybe it's a Gaussian, then you can write it as a deterministic function of some Gaussian noise, where the Gaussian noise is independent of the state. For discrete, for categorical actions, there's also ways to set it up that are a little bit more involved, but basically it's quite possible to set up this graph. So then you can use sort of the model-based reinforcement learning version 2.0 algorithm from Monday, where you collect some data, fit your dynamics, backpropagate through the dynamics to get the policy, and then you need to deal with the distribution mismatch problem, so you rerun the policy, collect more data, and repeat this in a loop. So that seems like a reasonable way to get a policy. That's actually what was used in that colored blocks paper. But unfortunately, there are some problems. So what's the problem with backpropagating into the policy? Well, do any of you guys have any thoughts about this? Any ideas about what some of the things that might go wrong could be? Yes?
Well, there might be a mismatch between our model and the reality.
Right, so there might be a mismatch between the model and reality. Hopefully, if you go through this loop often enough and your model is sort of capable of representing reality, that mismatch might be mitigated, but that could definitely cause some issues here. Any other ideas? Yes?
Is it that maybe the policy is like tied across all the time steps?
The policy is tied across all the time steps, yes. And this is getting at kind of a little bit of a computational issue here. So if you remember when we talked about trajectory optimization last week, we saw that we could use kind of this really convenient dynamic programming second-order method to compute the actions, and that was exploiting the fact that you can choose the actions at time step t completely independently of time step t minus 1. So you can fix your linear feedback law at time step t and then go back one step and know that that law is not going to change. But because the policy parameters couple the policy across all the time steps, now you can't use this convenient dynamic programming stuff. You have to do something that's a little bit more messy. And it's still theoretically sound. You can still compute a gradient, but it turns out to numerically be a bit problematic. So intuitively, the problem looks something like this, that the action you take over here in the first time step is going to affect everything that happens later. So the gradient over here is going to be kind of big, meaning that like kind of small changes to theta are going to affect this action by some amount, but that'll affect future states by a bigger amount. Whereas here in the back of the trajectory, the same kind of change to theta will result in the same kind of rough magnitude change to u, but it will change the total cost by comparatively less because there's only one state after it. So the gradient is much more sensitive at the beginning of the trajectory than it is towards the end. And that's actually why for the trajectory optimization stuff last week, we used these second-order methods. So, and this is coming back to this kind of shooting method view of things. So if you remember last week, we talked about how there's shooting methods and collocation methods for trajectory optimization. And in a shooting method, the variables that you optimize are actions. Here, the variables you optimize are the policy parameters, which determine the actions. So this kind of backpropagation approach is a lot more like a shooting method. And that had this problem that you kind of change the action a little bit at the beginning, and it sort of wiggles the whole remainder of this trajectory by some pretty large amount. So if you're familiar with the kind of optimal control and trajectory optimization, this kind of has a similar sensitivity issue as shooting methods. But there's no longer this convenient second-order dynamic programming style stuff that you can do because the policy parameters couple all the time steps together. So no dynamic programming. If you're more familiar with kind of the recurrent neural networks and backpropagation through time style optimization problems, it's actually a similar picture. So you can, if you kind of know, if you've worked a little bit with RNNs, then you can kind of pretend that this whole thing is actually just like one giant recurrent neural network. But unlike the kind of recurrent neural networks that we use today that have convenient properties like LSTMs where the gradients through time tend to be pretty nice. Here, this is sort of an arbitrarily nasty recurrent network where these are just arbitrary functions. And in general, this leaves you very vulnerable to vanishing and exploding gradients. So unlike the LSTM, we can't just choose like a model of, we can't just choose a dynamics that makes everything nice because the dynamics have to reflect nature. The dynamics can be quite messy, and the backpropagation through this can be quite problematic. And in fact, for complex systems, they need to be kind of messy because the real world is messy. So you might have discontinuities, sudden changes in velocity, and so on. So it's not that this is impossible to do. It's just that for some systems, computing kind of first-order gradients like this and doing gradient descent can be numerically problematic. And these problems are exacerbated in stochastic systems. So if you imagine that, let's say, you're trying to drive around a tree and a small change in your action will change you from driving around the tree to actually colliding with the tree, that's a very sudden discontinuous change. So trying to do kind of gradient descent on that can be tough. And in practice, it often actually doesn't quite work. OK, so that's sort of the numerical problems with backpropagating through the dynamics into the policy parameters and then directly optimizing the policy parameters. Does anybody have any questions about this? OK. All right, so we also learned last week that there are these things called collocation methods that I didn't get into too much, but I just mentioned a little bit of kind of a pictorial representation of it. So if you remember from the optimal control lecture, we had this sort of original constraint formulation of the optimal control problem where we're minimizing the cost. Our variables are the actions and the states are a function of the previous state in action. And then when we derived LQR, we first collapsed all of this into an unconstrained problem by basically substituting this equation for xt inside the sum, so the constraint went away. But we don't have to do that. We could also try to work with the original constraint formulation, where the x's and the u's are our optimization variables, and that's the sort of collocation view of things. So because the x's are variables in this optimization, you can just move the individual x's up and down. You just have to make sure that the constraint is satisfied. And there's all sorts of ways to solve these problems. You could, for example, relax the constraints and try to enforce them softly, or try to use some dual variables to enforce constraint satisfaction, or you can use sequential quadratic programming. That's a very popular choice, where you linearize the constraints and make a quadratic approximation to the objective. So there are a number of ways of dealing with this, and they do tend to be a little bit more well-behaved numerically, because the action is not kind of waving the tail of this trajectory around. You get to optimize over the states and the actions together. So these types of techniques for trajectory optimization sometimes tend to be a little bit more well-behaved numerically, typically more expensive computationally. So can we borrow the same idea when it comes to optimizing the policy? So can we say we'll have our states and our actions and our policy parameters as our optimization variables, and we'll just add a constraint that says that the action at time t is the action that your policy wants to take. So this is sort of extending the collocation view of trajectory optimization to policy optimization. Say, okay, now we'll have this additional variable, the policy parameters, and we just want the actions to be the actions the policy wants to take. And again, we can extend this to a stochastic view of things with things like the reparameterization trick, and I'll discuss stochastic stuff a little bit more later. So does anybody have any questions about this idea of setting it up as a constraint optimization problem? OK. All right, so now we need a way to actually solve this constraint optimization. We're going to kind of abstract things away a little bit, because this constraint of the next state is a function of the current state in action. We actually don't care that much about it. We can still take this thing and substitute inside the cost. The important thing is this constraint, right? So we can just say that really what we're doing here is we have some generic trajectory optimization, which we can solve however we want, whether it's using LQR or not. But we have to make sure that we enforce this constraint, that whatever actions that trajectory optimization procedure takes are going to be equal to the actions that your policy wants to take. So then this thing we can replace with whatever planning or control box that you want. So really the question is, how can we impose constraints on trajectory optimization or on a planner? So let's review a little bit from Monday, a particular method that we learned about for imposing constraints, and that's the dual gradient descent approach. So on Monday, we covered this method called dual gradient descent, where if you have some constraint optimization problem, so you're minimizing some function f of x with respect to x, and you have a constraint that says c of x is equal to 0, you can write down the Lagrangian. You can write down the dual, where in the dual, you just have to use the optimal x for the current value of the Lagrange multiplier. And then the gradient of the dual turns out to just be the gradient of the Lagrangian with respect to lambda, but evaluated at the point x star, which is the best x for the current lambda. So that yielded this really nice kind of algorithm that we could use to solve a constraint optimization problem using only a collection of unconstrained optimization. So first you find the best x for your current value of the Lagrange multiplier. Then you compute this gradient by differentiating the Lagrangian with respect to the Lagrange multiplier, and take a gradient ascent step and then repeat. So now there's no more, all these operations involve only unconstrained optimization and relatively simple operations, but it solves the original constraint problem in the end. So that's the approach that we can actually try to use here. But before we do that, there's a small tweak that we can introduce to dual gradient descent that actually makes it much more well-behaved in practice, and I just wanted to mention this. So this is sometimes referred to as the augmented Lagrangian. The idea is this, that this here is the Lagrangian that we all kind of know about, but you can actually write an alternative, what's called an augmented Lagrangian, where you add a little term here that says, in addition to having this Lagrange multiplier times the constraint, you're also going to have some constant times the magnitude of the constraint violation. So the constraint is c of x equals 0, and you're just going to put an L2 penalty on c of x. If the constraint was c of x equals a, this would be the L2 norm of c of x minus a. So you can think of this as sort of like a soft loss that discourages constraint violation. You can actually, it's perfectly fine to add this because at convergence, when the constraint is satisfied, this term vanishes, right? Because at convergence, c of x is equal to 0, so that term goes away. And before convergence, it can be really convenient because it can make things a little bit more well-behaved. So this is a linear term, and if you're far away from the right Lagrange multiplier, this linear term might cause things to kind of blow up a little bit, whereas this will always keep the constraint violation pretty small, especially in problems that are non-convex. So these are, the dual gradient descent, you can give nice guarantees for convex optimization problems. For non-convex problems, it's a little tougher. But empirically, for non-convex problems, the augmented Lagrangian approach tends to behave substantially better. So the procedure, exactly the same. Find the best x with respect to the augmented Lagrangian for your current Lagrange multipliers, compute the gradient, and take a gradient ascent step. So it still converges to the correct solution. When far from the solution, the quadratic term tends to improve stability because it keeps your constraint from being violated too much. And this is, those of you that have heard about the alternating direction method of multipliers or ADMM, this is actually very closely related to ADMM. So ADMM is sort of this type of method applied to the case where you have two variables and an equality constraint between them, or some kind of, in general, some sort of linear constraint between them. OK, so any questions about augmented Lagrangian? OK, great. So now let's come back to our trajectory optimization with the policy problem. So our problem, rewritten in more simple terms, is that we want to minimize the cost of some trajectory, and this hiding inside this min c of tau is really this sum over time with the constraint that the next state is a function of the previous state in action. So we want to minimize the cost of some trajectory, subject to a constraint that the actions along that trajectory are the actions that the policy would have actually taken. So we can write out the Lagrangian of this. So now there's two primal variables. There's tau and theta, and really tau is this big long tuple of all the states and all the actions. But we can write out the Lagrangian, and that's just c of tau plus the sum over all the time steps of these constraints. So Lagrange multiplier times pi theta xt minus ut. We can write out the augmented Lagrangian, which is kind of neat because now we have this squared error between the actions. If the action has more than one dimension, this would be an L2 norm. So now things are starting to look kind of quite sensible. We have our augmented Lagrangian, and then we use this the procedure from dual gradient descent. We have two primal variables, and technically we need to optimize the Lagrangian with respect to both of them to convergence. But it turns out that we can actually show, I'm not going to go through this in the slides, but we can actually show that it's still fine if you just do this in kind of block ascent fashion. So you first minimize with respect to the trajectory, then you minimize with respect to the policy parameters, and then you can actually increment your dual variable right away. It turns out that this actually still makes sense. But you can also just jump between these two up to convergence if you want, or you can increment the dual variable right away here. So that's the kind of dual gradient descent with the augmented Lagrangian applied to this constraint optimization problem. And these two steps have a very natural kind of interpretation. So first, we're going to optimize for a trajectory with this modified cost that says don't go too far from your policy. And we can do that using our favorite optimal control method. We can do that using iterative LQR. We can do that using sequential quadratic programming, whatever optimal control method you'd like to use. And then in step 2, we're going to say, OK, now we have this good trajectory. So now let's find the policy parameters theta that will minimize the Lagrangian. And the only parts of the Lagrangian that depend on theta are this term and this term. So this actually corresponds to, in this case, an L2 loss on the output of your policy. So this is a linear term. This is a quadratic term. So together, this thing is actually quadratic. So this is just essentially a weighted Euclidean loss on the output of your policy. So if your policy is a neural network, you just put that weighted Euclidean loss at the end of your network and train it with your favorite automatic differentiation package using stochastic gradient descent. So that's kind of neat. So you have trajectory optimization, supervised learning, increment the dual variables. And this is, and there are many variants on this algorithm that we can come up with for different kinds of policies, different kinds of trajectories. But they all have this general flavor of saying, first, let's find our trajectories, make sure they don't wander too far away from our policy, and then update the policy to try to match those trajectories. And on Monday, actually, Igor Mordich from OpenAI will come and give a talk about some of his work that actually uses kind of some really interesting choices for the trajectory optimizer and for the policy with this type of approach. Okay, so let's have some discussion about this method, which I'm going to term guided policy search. It's been called kind of different things in the literature, but all the instantiations of it have kind of roughly this form at a high level. So it can be interpreted as a constrained trajectory optimization method, meaning we're optimizing a trajectory up here, and we have some constraints which are being enforced with some kind of procedure like dual gradient descent. By the way, you don't actually have to break up step 1 and step 2. If you have if you're not averse to high-dimensional optimization problems, you can even combine step 1 and step 2 into one, so you can simultaneously optimize over both your trajectory and your policy with that Lagrangian. So it can be interpreted as a constrained optimization method. It can be also interpreted as imitation of an optimal control expert, because step 2 is just supervised learning. So this is really just imitating that trajectory. It's saying try to regress onto the actions that your optimal control expert took. So the step 2 can be viewed as imitation learning, and step 1 can be viewed as generating the data for imitation. So this is the connection between backpropagating to the policy and imitation learning. So the optimal control teacher here, unlike in standard imitation learning, the teacher actually adapts to the learner. So if the learner in step 2 is unable to copy some action, eventually in order to drive the constraint violation down to 0, the teacher, the optimal control algorithm in step 1, will need to change their behavior so that it's actually learnable. So this avoids actions that the learner can't mimic. And I'll come back to this point at the end of the lecture when I talk about trade-offs between different ways of imitating optimal control. Okay, does anybody have any questions about the guided policy search algorithm and the generic form presented here? Okay. Was there a question?
Yeah, what tends to come up as something that a learner can't learn?
Right, so what tends to come up as something that a learner can't learn? That's a very good question. So later on in the lecture, I'll talk about what happens in partially observed problems. And in partially observed problems, sometimes your teacher can take actions for which there's sort of no plausible explanation from the observations in the environment. Because if you're optimizing a trajectory, you optimize the trajectory using the actual states. So if you remember the distinction between states and observations, if I'm, let's say, walking to another room around the corner, I know maybe my trajectory optimizer knows that there's a person on the other side of that door, so I'm not going to, I'm going to go around the other side. But if I'm then trying to train a policy from color images, it just has no idea why this happened. So it might never be able to copy that, and this would cause the teacher here to change their behavior to be understandable. All right. So the kind of more general scheme of guided policy search, the one I presented on this slide is sort of the version for deterministic policies and dynamics and so on. The more generic scheme is that in step 1, we would optimize some trajectory distribution, because if we have, let's say, stochastic dynamics or stochastic policies, now it's not just one trajectory or a collection of discrete trajectories, it might be a trajectory distribution. So we might optimize some trajectory distribution with respect to a surrogate cost C tilde, which is the original cost plus some terms that discourage constraint violation. Then in step 2, we would optimize the policy parameters with respect to some supervised objective that tries to copy P tilde. And then in step 3, we might increment or modify whatever dual variables we have. So this is kind of the more generic version of this, where maybe it's no longer one trajectory, but maybe a trajectory distribution, and things can be a little more generic. So in general, we need to choose the following things in order to use this method. We need to choose the form of P of tau. So if everything is deterministic, then P of tau is just a collection of these delta functions. It says, probability 1 for this trajectory, and this one, and everything else is 0. That's the deterministic case. We can have a softer stochastic case, or maybe we have Gaussian distributions over trajectories, or something else. So we'll talk about some choices there. We need to choose a method of optimizing P of tau. So in the kind of version I showed on the previous slide, I said maybe use ILQR. So that's one choice, but in general, whatever will optimize the surrogate objective for P of tau can do the job here. So there are many different choices you can make. We need to choose the surrogate cost. So this, in general, corresponds to your choice of how you'll enforce your constraint. You can enforce the constraint using the dual gradient descent approach with these Lagrange multipliers. You can use the augmented Lagrangian. You could even use just a soft penalty method. So you could, for example, go back to the augmented Lagrangian, remove the linear term, and just leave the L2 term. That technically would not converge to perfect constraint satisfaction, but might be good enough in many cases. So you could use kind of a more heuristic penalty method. And there are other choices you can make. And then you need to choose a supervised objective for your policy. So you need to make some choice for these things, and depending on what you choose, you'll have algorithms with slightly different properties, slightly different convergence results, and also slightly different behavior for real-world tasks. So let me just kind of to illustrate this point a little bit, let me walk you through a different version of this algorithm for a slightly different choice for those four things. So we saw the version for the deterministic case. Now let's talk about a version of this algorithm for a stochastic case. So the version that I'll present to you here is the stochastic case where the trajectory distribution P is actually a Gaussian distribution. And this is going to build on this local models method that I showed in Monday's lecture. So for that local models method, if you remember, we were generating our rollouts from a stochastic controller that was time-varying linear Gaussian, meaning that at every time step, the action is a linear function of the state, which is what we get from LQR, and there's some covariance, which, as we saw, we can set to the inverse of the Q function curvature. So this is just one choice of this, but because it's linear Gaussian, it induces a Gaussian trajectory distribution. So now, again, the story is the same as on the previous slide. You optimize your P of tau with respect to some surrogate cost. And we saw on Monday that we can optimize this P of tau using LQR. If we choose the covariance correctly, the surrogate cost would include all those dual variables and so on. We optimize theta with respect to some supervised objective, which is going to be just a regression onto the rollouts that we get from running this in the real world. And then we increment or modify the dual variables. So exactly the same algorithm structure, but now we can actually use this method with learned local models and this particular form of the trajectory distribution. So when we optimize P of tau with respect to some surrogate cost, what we're really doing, as we discussed on Monday, is that we're minimizing the sum of these expected surrogate costs. And now we have another constraint inside number one, which is to stay close to your old trajectory distribution. So basically, the method is modular. So into step one, you can substitute whatever your trajectory optimization procedure is, including the one from Monday, which itself has a constraint inside of it. So even though this is a constraint that we might enforce with dual gradient descent, that's sort of an inner loop, completely separate from the outer loop that actually enforces agreement with a policy. So we can just substitute that thing in there, and just like the method that we derived on Monday, we can just do that in step one, and all we have to do is then add another step two to regress onto those actions using our policy. So just to illustrate this graphically, on Monday we saw this approach for optimizing trajectories. So we generate samples from our current controller. That's our collection of trajectories. We use those trajectories to fit dynamics with linear regression at every time step, or maybe Bayesian linear regression if we have a prior. Use that to improve our trajectory distribution with the constraint that says don't go too far from your old one so that your dynamics are not violated too much, and then repeat the process. So this is exactly what we saw on Monday. And now we just have to add that additional step of training our policy to mimic the behavior of this optimal controller, and that just comes in over here. So we sampled some data, and now we're going to also use that data to train our complicated neural network policy to take the same actions from the states or observations that were encountered by this guy. And that's also added as a surrogate cost in the improvement step. So this is sort of the schematic illustration of this method. But this is just a schematic that illustrates exactly this three-step procedure where, obviously most of the complexity is in step one, and then step two just adds this little side thing, but this is the thing that actually does all the action. That's the thing that actually makes your policy. All right, so does this picture make sense? Does anyone have any questions or comments about this? Okay, great. So this is sort of one instantiation of this method for the case of unknown dynamics, local linear models, and stochastic policies and trajectory distributions. And there are other ways to instantiate this method. So let me give you an example of this thing kind of in action and tell you a little bit about some of the things we can do with it. So I'm going to give you a robotics example that's going to use this method in the following way. So in this robotics example, what we're going to try to do is we're going to try to build a policy that takes actions based on images from the robot's camera. And instead of training the policy on just one trajectory distribution, we'll actually train it on a collection of trajectory distributions. So over here, in step one, we can just generate samples from multiple different controllers, fit dynamics for each one of them, improve each of them independently, but use all of them together to train a single policy. And that's pretty convenient because optimizing a separate trajectory for sort of different instances of the task, that's that's pretty straightforward. But then if you combine them into a single policy, you get better generalization. So here's how we can instantiate this method. Let's say that we'd like to have a task where the robot puts this little red shape into a shape sorting cube. So we just insert that red shape into a hole. And we want to be able to use vision to localize where this object is. So what we can do is we can position the object, the wooden block, we can actually have the robot position in different places. And for each of these places, we're going to optimize a separate trajectory distribution. So for each one of them, we're going to fit a different linear dynamics, a different p of u, ut given xt, and so on. So those are done completely independently, completely in parallel. But then we'll unify that into a single policy so that it can deal with all these different positions and then generalize to new ones. So we have a collection of trajectories that we're building here. And this is kind of what the process looks like. Remember that it's using fitted local linear models, so it needs to keep making these rollouts to estimate the local dynamics, and that's what it's doing in this video. And then all that data is combined to train a single global policy. And of course, we have to enforce the constraint, so we have to iterate this process. So we have to train our policy in step 2, increment some dual variables in step 3, and then come back and update our trajectories in step 1. So as we go around in this loop, the constraint is enforced more and more, and we get to, yes, there's a question?
Yeah, so in these examples, you have to define your trajectory before you actually handle the problem, right? So for example, in this robotics case, you have to make the model of what the robot's supposed to do, correct?
So the question is, you have to define your trajectory in advance. So you have to make a model of what the robot is supposed to do. So yeah, good question. You have to define a cost function. So the trajectory is constructed to minimize some cost function. The cost function in this little example is just the distance between where the shape currently is and where it needs to go. But you need some way to evaluate that cost function. And that's actually a very important point. And that's coming back to something I mentioned in the, I believe, in the first optimal control lecture, which is that you need some way to evaluate your reward function. And sometimes in kind of real-world robotics cases or other cyber-physical systems, that can actually be highly non-trivial. So we're assuming you have some way to get your cost. Later on in the class, Chelsea will talk about inverse reinforcement learning and some other ways that we can get a cost function if we don't know it. All right, and then the benefit of building this thing, you kind of might wonder why we go through all this trouble. The benefit of actually building this thing comes back to some of the stuff I mentioned at the beginning of the lecture, which is that you can get good generalization and so forth. So you could, for example, generalize to new situations where the block is in an unknown position. Maybe the robot is not holding it anymore, and so on. So let's talk about that a little bit more. Let's talk about this generalization stuff a little bit. One of the things that you can actually do with these kinds of approaches is you can use this kind of input remapping trick, which is kind of, it's a little bit of a subtle point, and it comes back to this distinction between states and observations that we discussed in the imitation learning lecture. There's a question?
Yeah, real quick. So in that example, is the local linear model in pixel space?
No. So that's actually what I was about to talk about. Yes. So the local, so trajectory optimization requires you to have a notion of state. And the state here is the position of the arm, of the object, and so on. So the trajectory optimization is not being done on the images. It's just being done on the kind of known state of the system. And this is actually kind of one of the things this method is exploiting in order to work well. So this is the problem that I wrote down before for you. And you notice that there's no observations in here at all. So everything here is using the state, and it's because you need the state to evaluate the cost. You need to use the state in here to build your controller. LQR requires knowing the state. So this is all assuming that you have the state of the system. And if you remember from the imitation learning lecture, the distinction between states and observations formally is that the states satisfy the Markov property, the observations in general do not. So if you have an image of the scene that doesn't necessarily satisfy the Markov property, if your arm occludes some object, you may not actually be able to tell where it is. The observations are not Markovian, but the state is. So this is all in terms of the state. However, the policy pi theta here doesn't have to be in terms of the state. It can be in terms of the observation. The observations in general, you assume them to be some function of x. So it's OK to replace x with some function of x in here, because you can just say, OK, this is sort of part of my policy. The way my policy works is that it looks at the state, converts that state into an observation, and then processes the observation. It just so happens that you don't know the function that converts a state into an observation, but it's still in there. So you can easily replace this x with an O, and everything is still good, but this is still an x. So what this is really saying is optimize your trajectories in state space, but then train your policy so that it can reproduce the behavior of those trajectories only from the observations. So that means that this stuff over here with the trajectory optimization is relatively easy because we have the state, and when the block is always in the same place for trajectory number 1 and always in the same place for trajectory number 2 and for trajectory number 3, it doesn't really need vision in order to optimize those trajectories. But when you force the neural net here to deal with the raw observations, it has to basically understand what these guys over here did in terms of the images. So one instantiation of this input remapping trick is that at training time you have the full state, which you use to do your trajectory optimization. But for the policy, you only give it the observations, so that at test time, you can just perform the task using only observations. And this will come up again in another method that I'll discuss later in the lecture. So this is kind of quite a neat idea when you imitate optimal control. Yes?
In your state, do you only consider the position or also velocity acceleration?
So for this task, the full state is actually the joint angles of the arm, the position of the end effector, and their time derivatives. So the velocities. Okay, so does anybody have any questions about this, this concept? Yes?
Does the position where you want to end up also enter in your observation, or it's only reflecting the cost?
So you can do it either way. In these experiments, it only enters into the cost.
Because like when you after feed the policy that takes in the observation, it has a notion of which of the different tasks it's doing, right?
Yeah, of course. So here, for this little thing that I showed a video of before, the task is always to put something into the hole there. But if you have, let's say, maybe you have a more parameterized scale where your system might be asked to do many different things, then yeah, you need to somehow tell it that. I mean, in general, I should say the algorithm itself, I mean, everything is kind of perfectly well defined regardless of what O is. O might even be just completely empty. It's just that you will not be able to do very well at the task in that case, but you'll sort of, in general, under unreasonable convexity assumptions, it should still do the right thing as well as it can under that parameterization. Of course, in practice, you have local optima and so on. Yes?
I have a more general question. When we say guided policy search
Mhm.
versus policy search,
Yep.
what's the major distinction there?
It's a particular policy search method that consists of that funny iterative procedure. Yeah. And we'll learn more about different policy search methods also in the model-free RL lectures later in the course. So this is a kind of a model-based policy search procedure. Yes?
In this case, what is OT exactly?
So in this case, OT is the image from the camera and the joint angles and their velocities.
So in your training time, you are training a full instrumented environment, which you have all the things.
Well, it's sort of like, it's instrumented in the sense that this thing is all, like for trajectory number 1, the hole is always right here. So it's instrumented in the sense that it's consistent. So it's sort of like almost like a dual decomposition type idea. In general, you can instrument it any other way you want. You could, for example, put a sensor on the cube and try to localize its position. That would be a fine way to do it here. Here, sort of the instrumentation is just set the environment up exactly the same way each time for that trajectory. So trajectory number 1 always sees this. Trajectory number 2 always sees that. And we'll actually get back to this question of instrumentation later on for another method I'll describe. Okay, so that's kind of this input remapping idea. So this, I'll show you a video of this kind of to illustrate this thing in action because it's kind of neat to watch. But basically, on the policy side, the short version is that it's a policy that's going to take in images and a little bit of the robot's encoder information from the arm. It's a convolutional network that processes the images kind of the way we might expect. It outputs a vector of torques, and those torques are sent to the arm. So this is sort of a generic kind of convolutional neural network type policy, and we'll see more of these again and again in the course. Okay, so this is kind of a little case study of this method being applied to a robotic system. This is a paper that we had on this, and mainly I just want to show you some of the videos and point to some of the neat stuff that's going on. So let's see if this video will play. All right, so this is that task that I described, and here this is actually just test time, so this is using the vision-based policy. This is another task where the robot has to hang the coat hanger for a rack that's different distances from the robot. This is a task where the robot actually has to watch its own gripper, so you see that the angle of the hammer that it's holding, it's a different angle, so it has to watch its own hand. And this one involves having to spin the cap to actually put it on the bottle. And then after this, oh, I guess I don't have the videos with the first-person view. Okay, maybe I'll show them at the end of the lecture, but I also have some clips that show the first-person view of the robot. So anyway, some neat kind of vision-based stuff. Now, that was imitation learning where you have this kind of optimal control in the loop with the policy optimization. You're actually modifying the trajectories or the trajectory distributions to best suit the policy optimization procedure. Now, we could also take this idea and say, OK, we kind of derived this imitation learning of optimal control starting from the model-based RL view. But it seems like imitating optimal control is a good idea in general. What if we use other imitation learning methods? Which is a very reasonable way to go about this. So for example, if we learn about Dagger, that's a pretty nice way to do imitation learning. That's pretty simple, and that's what you guys are actually doing for your homework. We could use Dagger just as well. So we could say, let's do imitation learning with Dagger without having to do any of the surrogate objective stuff, and use, let's say, our favorite planner if we have a discrete environment. And that's in fact what was done in this paper that I mentioned earlier in the class, where the idea is to learn to play Atari games without having to deal with the usual sort of Q-learning stuff, and just use a model-based planner. So in this work, they're using Monte Carlo tree search, where the objective is just to play the Atari game successfully. So the planner is not adapting to the policy, and instead they're dealing with the distribution mismatch by using Dagger. So that's a very sensible thing to do, and I'll mention at the end sort of what the different trade-offs between these actually are. But before I get into that, let me present one more algorithm that kind of deals with a particular issue that Dagger has. So using Dagger to do imitation learning for optimal control, quite a nice idea. The algorithm is pretty simple, but it has a little bit of a problem. And the problem is this. So we can get rid of the human. We can ask the computer to label the actions. But we still have this problem that we need to run our policy in the real world. And the policy might not be very good. So initially. At the end, it's going to be good. But initially, when we're just starting out, maybe the data set from the human is very different from what we're able to mimic, and our initial policy is bad. So we get, our autonomous car does stuff like that. So sometimes this is OK. Sometimes it's OK to have your robot do some crazy stuff, or to have your whatever your autonomous system is do some crazy stuff. But sometimes we'd like to avoid it. Sometimes we're in sort of a safety critical domain. And it turns out that we can actually avoid that step. We can actually avoid running bad policies in the real world by imitating optimal control and sort of using that optimal control technique a little more judiciously. So here, instead of using the method with learned local models, we're actually going to assume that the model is given to us from somewhere else. Maybe we learn the model. Maybe we just know what it is. And we're just going to deal with the control part. And the way we're going to do control is using model predictive control. So if you remember from before, model predictive control is where we replan the actions every time step. Here, we don't really care how you're replanning the actions. Maybe you're using LQR. Maybe you're using some discrete planner. But you have some way to replan the actions every time step. And we're going to use that to avoid needing to directly run a partially trained policy. So what we're going to do instead is we're going to run this thing called pi hat. And what pi hat is it's maybe in the continuous case it's some time varying linear thing that doesn't really matter so much. The important thing about pi hat is it's going to minimize a particular kind of modified cost function. So the cost function for pi hat, this is done with MPC, so we recompute this every time step. The cost function for pi hat is the part we expect, which is minimizing cost, plus this additional new part, which is going to be the KL divergence between pi hat and pi theta. So pi theta is the policy that you're learning. KL divergence is a measure of how different two distributions are. So what this is saying is pi hat shouldn't be too different from pi theta, and how much we care about this is determined by this constant lambda. OK, so let's unpack this a little bit. What this means is that if you're controlling your system, and at a particular time step you see some image, let's say, or some other kind of observation, and your partially trained policy pi theta wants to take some action. So maybe here pi theta says, oh, I want to drive the car forward. You plug that pi theta into this objective. You run your planner or your trajectory optimizer to choose a new policy pi hat that minimizes the cost that you will get for your trajectory plus the KL divergence against pi theta at this current time step. And maybe pi hat says, OK, if you drive forward, that's good because this term will be small. But maybe there's a tree right in front of you, so the cost will be big. So this is going to say, OK, you can't go forward. I'm sorry. Like, the cost will just be too high. So I'll just do something that's sort of as close as possible to what you're trying to do, but also minimizes this cost. So it's basically saying, take actions that are as close to what pi theta wants, but that also minimize the cost. So if you have some really bad cost, you're actually going to override that policy. So this is an idea that's kind of a little bit similar to the surrogate cost that we saw for guided policy search earlier, except now it's in MPC mode and within this kind of Dagger framework. And then, of course, it's MPC, so when you actually take that action, you might observe a new observation. Maybe now pi theta changes its mind and says, oh, now I really want to go right. And you just plug that in here again, crunch through the optimization, and get a new action. And then that replans your path. And then you proceed.
Why don't you just use the pure MPC?
Well, so the reason that you could use pure MPC to just drive the car. So the goal of this whole procedure is to get a policy pi theta. And the reason that you might actually prefer having pi theta at the end is basically all the same reasons as before. So if you want something that is faster to run at test time, if you want to run it from pure observations at test time, whereas you only have the states at training time and so on. So I'll talk about that a little bit on the next slide. So one of the reasons actually that you might want to do this is the input remapping trick, right? So over here in the scale divergence, your policy pi theta might depend on the observations, but pi hat, in order to run MPC, you need the full state. So what you might do, for example, is you might have pi theta that controls your system from, let's say, images or raw sensory data, and your MPC, your planning is done from states. So the distinction between states and observations, I've already mentioned this a few times. It's the Markov property. So you could, for example, imagine that you have some external observer at training time. Maybe if you have a car, maybe it's driving on an instrument to track. There's somebody that tells you, here's what your state is, so you can run your MPC, or maybe it's an environment that you've mapped in advance so that you know where the obstacles are. Something that basically lets you run MPC. If you have that, then you can use that state to perform this optimization down here. And then the dynamics are either known or you get them from some learned model. But crucially, in this procedure, the observation distribution is not known. So the observation distribution is, maybe if you're using images or LiDAR, this is sort of how does your state produce images, or how does your state produce LiDAR readings. This is in general something really complicated. So if you don't know what that is, this procedure would work. And it basically amounts to saying, I can predict what states I'm going to visit so that I can evaluate the cost. And if your cost depends on, let's say, your car colliding with something, maybe your state includes, is your car colliding with something, or the positions of obstacles. But the observations might be unknown. And that's actually OK here, because if you notice the form of the subjective, the KL divergence is just against pi theta at the current step t, whereas the cost is at all the steps t prime from t to capital T, which is your horizon. So you're sort of, you're only minimizing the discrepancy against what your policy is doing right now, but you're planning for a low cost for that entire trajectory. And that's why you might replan when you go to the next time step, because when you go to the next time step, you get a new observation, and maybe pi theta now will want to do something else. Yes?
Wait, how is the computer labeling with the correct action in step 3?
Step 3? It's solving this optimization problem. Oh, you mean for the data set. So for the data set, there are actually a few choices you can make that all end up converging to the same answer. The default choice is actually to just use whatever your expert is. So if your expert is MPC, you just remove this term and just solve the real kind of optimal control problem. And then you get an optimal action. And that's a perfectly reasonable way to do it. So step 3 is sort of, it's unchanged from before. It's just use your expert. So pi hat is not your expert. Pi hat is just the policy that you're executing in the real world. So in classic Dagger, step 2 would be to run pi theta, actually, your learned policy. And now we're actually running something that's sort of somewhere between the expert, which would minimize this, and the learned policy, which would be this, and we're sort of blending them a little bit. Yes?
So in this case, do we kind of have two experts, the human and the MPC?
Actually, so this step 1, this is a typo. This should, you can get this data from wherever you want. It doesn't have to be a human. So this is a good question. You could initialize it with human data, or you could just run MPC from the start to get initial data. So you just need some way to get something up here to initialize this thing. Yeah. Any other questions? Yes?
So in this case, you're not doing the replanning at every step.
You are, yeah. So every step you replan, it's just that you replan sort of using the long horizon cost, but greedily with respect to this term. So this term is not considering the future consequences, which is important because you don't know what the future observations are going to be. Okay. So here's sort of an example of this thing, in a simulated experiment to kind of show you maybe one of the ways we might use a method like this. So here we're going to have this objective. We're going to use the input substitution trick. So we have, you can imagine this is a quadrotor. It's flying through some environment with obstacles. And maybe at training time, we have some kind of way to localize the quadrotor. Maybe we have motion capture cameras looking at it or something like that. So that gives us the state. The observation is just the onboard measurements. Maybe there's a LiDAR on it, or maybe there's a camera. And this term right here is going to basically be the thing that encourages pi hat to take actions similar to pi theta. So the way this might work out in practice is that if your quadrotor is flying towards an obstacle and pi theta decides I really want to plow into this obstacle, then even though you'll incur a loss over here by violating that desire, you'll do much better with respect to the cost. So you'll actually choose to override it in that case. You can show actually, and this is something that's in the paper on this work, that if your multiplier lambda is increased based on a schedule that satisfies some requirements, then you will still get sort of the usual Dagger convergence guarantees. So if you run this long enough, eventually your samples will be close enough to pi theta that the distribution mismatch trick, the distribution mismatch problem will not be an issue for you. But that requires some conditions on how you choose lambda. All right, so here's a video of a policy that was learned using this method. So this is a policy in simulation for a quadrotor flying through a forest using kind of a fan of laser rangefinders as its observation. So this is not images, this is actually kind of simulated LiDAR. And you can see it's kind of dodging these trees and so on. So this was trained using MPC with full state observation, and at test time it's using the onboard measurements. And this is using a simulated grayscale camera. Okay, so this is just sort of another example of a situation where you can imitate optimal control, get a policy that can process whatever observations you want. The policy is trained with supervised learning, and then you actually modify the behavior of your optimal control teacher to sort of provide, in this case, behaviors that are reasonably low cost at training time and conform a little bit to what your policy wants to do. Okay. So let's discuss a few of the different trade-offs between the methods that we learned about. So we talked about Dagger and guided policy search. The vanilla version of Dagger doesn't require an adaptive expert. So Dagger, in fact, the vanilla version of Dagger doesn't even care what your expert is, so long as the expert can provide labels for arbitrary states and observations. So any expert will do, so long as whatever states your learned policy visits can be labeled. And the other thing is that Dagger does assume that it's possible to match the expert's behavior up to a bounded loss. And this point is actually quite important. So especially in partially observed domains, your expert might do things that your policy has no way of replicating. And we can come up with actually a pathological example of this. Your policy can take anything as input. So if you just say, I'm going to kill all the input to my policy, so my policy doesn't get to see anything, it's just blind, then obviously you can't reproduce any kind of adaptive expert. So any expert that doesn't just take the same action or take actions randomly cannot be reproduced in that case. So in that case, the Dagger algorithm essentially wouldn't work. So formally, the assumption is that when you run supervised learning, you should be able to achieve a bounded loss on your data set. So bounded loss means that there is something that you can learn from the expert, and you can bound how wrong you are, regardless of which states and actions the expert showed you. That's a very important assumption, which oftentimes is a very, very reasonable assumption, but you have to be a little bit careful, especially in partially observed domains, because sometimes it can be violated. The guided policy search approach and the Plato approach, which is somewhere between the two, adapts the expert behavior. So adapting the expert doesn't require bounded loss on the expert, at least on the initial expert's behavior, because the expert will change to essentially make the behavior more learnable. But there's additional machinery that's actually required to perform this adaptation. So unlike Dagger, with guided policy search, you have to assume that you can actually modify your expert's behavior, and that involves a lot of, quite a bit of additional machinery on how that optimization procedure is actually going to be done, either using MPC as you saw in Plato, or using the the trajectory optimization procedure for the robotics example. So these are kind of the trade-offs between these two. So you need a bounded loss against whatever expert you have. Here you don't necessarily need that, but you need to be able to modify the expert. So does this kind of make sense to people? I think this is kind of quite an important slide as far as choosing which method to use and so on. Okay. So let's conclude a little bit and talk about and recap a little bit why we might want to use a method that imitates optimal control. One of the benefits, and I didn't get too much into this, but I'll talk about it now, is that generally these kinds of techniques are relatively stable and easy to use. So if you're in a domain where you can easily construct a planner or an optimal control algorithm that can generate ground truth data for you, these types of techniques are relatively stable and easy to use because once you have that planner, then the rest of it is just supervised learning. And supervised learning is something that we understand pretty well, so it's often kind of easy to get it up and running. Oftentimes, for example, in my work, even if you're in a setting where you don't necessarily expect to have a planner or optimal control method for the real system, it might still be very convenient, for example, to prototype your neural net architecture or something like that using one of these methods, because then you can quickly check whether the supervised learning procedure will get you a good policy. You can tweak your architecture and so on. And then once you're happy with it, if you're in a domain where you really want a model-free method, you can take that architecture and see if your model-free method will work. So kind of relatively stable and easy to use makes it good for prototyping because supervised learning works pretty well, and optimal control, in domains where you can use it, usually works reasonably well. The input remapping trick, so the ability to exploit the availability of additional information at training time, can be really convenient. So that can allow you to sort of quickly get solutions to a problem and then still be able to train up a policy that can use raw observations at test time. And it overcomes the optimization challenges of backpropagating to a policy directly if you want to use a model-based RL method. So that can be quite convenient. And we'll talk about, by the way, about model-based RL for some more complex situations, like cases where you have images and you want to actually predict those images later on in the course. But so far, when I've discussed model-based RL and backpropagating to the policy, what I really mean is you're operating on the state. Usually, these kinds of techniques are sample efficient and reasonably viable for real physical systems. This is not so much because they're imitating optimal control. It's really because model-based methods are efficient. So if you can train a model and it's a decent model for your system, usually that'll have better sample efficiency than model-free techniques, with the caveat that for some systems, training good models can be exceptionally difficult. Okay, so that's sort of the upshot. Now, what's the downside? Well, one of the downsides of model-based RL methods is that you need some kind of model. Sometimes that's relatively easy to get. Sometimes it can be very hard to get, especially if you're operating on raw observations. Building a model that predicts images accurately, that's very hard. Building a model that predicts high-dimensional LiDAR measurements can be hard. Or if you have a really complex physical system. So if you remember the example with the cup, with grasping the cup, there the physics of that task might be really complex, but the policy might be simple. So sometimes model-based RL is not a good choice because the model is much more complex. Not always available, sometimes harder to learn, and so on. Learning the model also takes time and data. Sometimes it takes less time or less data than learning a policy directly, as we'll see in the model-free lectures later on in the course. So sometimes expressive model classes, especially like neural nets, are actually not a great choice because even though they're very expressive, even though they can represent lots of functions, they might require a lot of data to learn those functions. So you might actually intentionally opt for a less expressive model class just so that we can learn more quickly. And it's important to try to understand which situation you're in. And sometimes fast model classes like linear models are not expressive enough. So striking that balance can be a little tough. And the other point about model-based RL methods is that sometimes they introduce some kind of additional assumptions. So for example, if we want to use the local linear models, that's nice because we don't need to build these global models. Everything is reasonably quick. But you're implicitly assuming when you do that you have a system that's continuous enough that you can actually approximate it with a locally linear model, which for some physical systems is a reasonable assumption, but for some systems that might not be a reasonable assumption. For the local linear models, you would assume that you can reset the system to the same or at least a sufficiently similar initial state so that multiple rollouts can be reasonably approximated with these Gaussian distributions. If you have a Gaussian process style model, like the one that we saw in the colored blocks example, that's sort of implicitly assuming that the dynamics of the system satisfy the assumptions of the GP, which in that case was smoothness. Again, not always something that holds. And for other systems, for discrete systems and so on, depending on which choice of model you have, usually there's some assumptions that are implicit in that. So be careful when you're dealing with things like that to understand the assumptions of your model class, the degree to which those assumptions are actually satisfied or not satisfied by your real physical system, and so forth. Does anybody have any questions about sort of the strengths and the weaknesses of model-based RL approaches and imitation of optimal control? Okay. And so forth. All right. So that's actually it for the first unit on model-based RL and imitation learning and optimal control. On Monday, we'll have a guest lecture from Igor Mordac from OpenAI. He's actually going to talk about some of his research, which will include some of the model-based RL stuff. And after that, we'll have a unit that will be taught by John Schulman on model-free RL. And I'll just give sort of a little bit of a preview of some of this. So while model-based RL can be viewed as kind of trying to understand the physics of the world and then find the optimal policy given that understanding, model-free RL ends up being a lot closer to kind of a trial and error style way of learning. The idea is that we could actually get a good behavior without actually understanding how our actions affect the next state by using a kind of trial and error. It ends up oftentimes being slower. Of course, not always. It depends on the particular situation you're in, but oftentimes slower, but oftentimes more general, because with trial and error learning, since you don't need to reason about the consequences of your actions directly as far as which states they affect, it can be more easily applied to kind of very peculiar systems with weird conditions. So that's coming up next, and kind of a little bit of intuition of how this trial and error learning might work is something like the following. If you have a particular guess at your current strategy, your current policy, you might run that policy in the real world, you get some trajectories from that policy, and then what you do is you simply look at which trajectories are better than others. So the green check mark here represents a very good trajectory, the red X represents a really bad one, and the yellow check mark represents something that's sort of mediocre. And then what you do is you say, well, my behavior is going to induce a distribution over trajectories, and I'm going to take the trajectories that were best, and I'm going to try to increase their probability. And I'm going to take the ones that are not so great, and I'm going to decrease their probability. And this is kind of the high-level intuition behind the way that trial and error learning, the model-free reinforcement learning actually works. So we'll see a number of different methods for doing this kind of reinforcement learning in the subsequent weeks. All right, so I'll see you all on Monday for the guest lecture.